First example I'd like to give you from 9.2 is a little bit like problem 18. This is problem 18. It asks us to find the union of these two sets. The union of two sets is a set that contains every element that's in either one, but you don't double count things. So for instance, 1 is in here in the first set, 2 is in here, and 4 is in here. So the union has to have 1, 2, and 4, but it also has to have these. Notice we don't put another 4 in. It's just everything that's in one or the other or both. So there's a 6 and there's an 8. So the union of two sets is a set that contains every single element of all the sets that you were taking the union of. But it doesn't count things twice. There wouldn't be two 4s in there. Here we have the same two sets, but now we're doing an intersection on the sets. The intersection of two sets is a set that contains anything that happens to appear in both of them. 1 is here but not here, so it's not in the intersection. 2 is here but not here, so it's not in the intersection. 4 is in both, and so the intersection of these two sets is 4. So that's an example of union and intersection of two sets. Second example is problem 34. I've called it A and B, but problem 34 is just this problem. And the thing to remember about OR is that it's union. So we want to have a picture or describe everything that is here, or both. And the easiest way to do that is to make pictures. So we have everything that's less than -5. Note, I put a few numbers around -5 in the correct order so that we know what we're doing. These are all the numbers that are smaller than -5. The empty circle indicates that -5 is not part of this set. Now we're going to union that with everything that is here, and that is all the numbers greater than 1. Now if you're a beginner at this, it might be helpful to, sort of make this thing match. So what does that mean? This isn't strictly speaking necessary, but it can help. These are all the numbers greater than 1. So now when you do the OR, when you try to get an answer to this kind of problem, you want all the numbers that are here, or any that are both. So what that's going to look like is it's going to look like all the numbers smaller than -5 combined with all the numbers bigger than 1. And so here's a picture, one possible picture of the union or the OR statement between these two groups of numbers. Now if we try to put this in interval notation, this left-hand side would be going left forever, and it starts at -5, and it does not include -5, so we use the parentheses. And then we could put OR, but it's a union, so let's use the union symbol from the previous section, and then we have all the numbers starting at 1 but not including 1, so we use the parentheses, and then it goes right forever. So this would be interval notation for the same group. Now what happens if we do this problem instead? Well, we will still have this graph, and we will still have this graph, but now when we combine these two graphs together, we're doing an AND. We're looking for numbers that are shaded in both of them. But there are no numbers that are smaller than -5 and greater than 2. So when we go to make a picture of all the numbers that are in both of them, the intersection, we don't get anything. We just have an empty number line. We have an empty set. It's empty. So the intersection is empty. And one way to put that is that the answer to this is empty. There's nothing. You could put a graph like this, where there's no points on it, but that's kind of ridiculous. You could try to do interval notation, something like this, but that's sort of ridiculous. So I think just putting an empty set would be best. In problem 54, we're asked to solve this and graph the solution set and put the solution in set builder notation and interval notation. So let's solve. Let's take away 1 from both sides. We're trying to isolate t. And then if -7 is less than or equal to t, that implies t is greater than or equal to -7. I like to have the variable on the left-hand side, and then we have an and here we can take away 8 from both sides, and we get t is less than -6. And these are being combined with an and so let's graph the first one. And that is everything greater than or equal to -7. And let's graph the second one. That is everything less than, strictly less than, -6. And then the and is the overlap if they're crunched together. Well, where are the points that are shaded in both? This one's shaded in both, the -7. All these are shaded in both, and then this one's not. So it looks as if the intersection, the and of these two groups of numbers is where they overlap, and it looks like they overlap at -7, and they continue overlapping, but then at -6 this one no longer is shaded, so it looks like it's this little piece. So how do we put that in set builder notation? Well, there's all kinds of ways to do it, but one way is to say the set of all x's such that, and then just describe this. So we could say that x is greater than -7, greater than or equal to -7, and at the same time x is less than -6, and that would do the job. Another way to do this in set builder notation is to put the set of all x's such that, and then just put the x here and surround it on the left with the smallest value and on the right with the biggest value, and then that locks the x's in between here, and we want to put less than or equal to because it can be equal to -7, and we want to put less than here because it can't be equal to -6. And the way this is read officially is the set of all x's such that -7 is less than or equal to x and x is less than -6. And so that's a couple different ways of writing this in set builder notation. Interval notation is probably the best because we put the far left number here, a comma, we put the far right number here. Here we use brackets because -7 is included. Here we use parentheses because -6 is not included. And this is all the numbers between -7 on the left and -6 on the right. It includes -7 and excludes -6. And so I like the picture because it tells me what's going on. I like interval notation because it's very simple to write. And set builder notation here is not my favorite. The algebra that we're learning has uses, and sometimes those uses are kind of obscure. So here we are in a section about inequalities and less thans and ands and stuff like that. And in problem 92 on page 591, they give you this problem and they say, let me just read the directions to you. For f of x as given, use interval notation to write the domain of f. So the domain of f is the numbers we can put in, and the numbers we put in go right here. So we're going to do 2 times a number minus 10, and if that's all there was, 2 times a number minus 10, we could have anything. But then we're taking the square root, and we can take the square root of 0, and we can take the square root of positive numbers, but we don't know how to take the square root of negative numbers. And so 2x minus 10, the amount that lives inside the square root thing, has to be greater than or equal to 0 for us to know what to do. because we can't take the square root of something that's less than 0. Adding 10 to both sides, we get this inequality. Dividing both sides by 2, we get this inequality. So for this to be a problem where we can work the square root out, x has to start out being greater than or equal to 5. Now, it says use interval notation, so the interval notation would be that 5 is on the left-hand side with a bracket, and then x is bigger than or equal to 5, so x goes right forever. And so this is interval notation. As long as x is 5 or bigger, we can find out what the function's value is by doing 2 times x minus 10 and taking the square root. But if x is smaller than 5, we can't do that. We get stuck. And so this would be a representation of the domain. This tells us what x numbers we can actually use in this function.